So I am everyone. I'm Renaud Dubois. I work at Ledger Innovation Team, and today we are going to talk about cryptographic, elliptic cryptography optimization for the Ethereum account abstraction. So I work at Ledger Innovation Team. Our mantra are self-custody, user experience, and security. We're a short team of 6 persons gathering all skills, hardware, software, cryptography. Hello, that's me. And you may wonder, why should I under this talk? Because I hate math, so don't panic. I will guide you through this, so you can speak about it later. So second part of the talk is account abstraction. It brings a way to implement your own cryptography, so this is the peak of self-custody. It could be used to improve user experience, for instance, using passkeys. We're going to talk about this later. And this requires, sorry for your loss, to implement yourself, your security, your cryptography. So you have to optimize this because this is very gas expensive. So this is the plan of the talk. Okay, so I'm gonna be really short about account abstraction, but because I'm sure that you're gonna hear a lot about it during this week. But mainly, what interests us for this talk is that basically account abstraction enables you to choose any cryptographic algorithm as your signing algorithm. So signers must be arbitrary logic. So, for instance, if your religion is that you cannot use a curve with a null discriminant, you can switch to another one. Okay, so this one you don't care. So what? But in fact, it means that all the problems that we face are solved, mainly user experience, governance, post-quantum resistance, problems such as inheritance, and it even makes the coffee. So let's give some use cases. So the fact that the signer may implement any signing protocol can be used to simplify the UX. There are different frameworks aiming at implementing WebAuthn. So WebAuthn, alias FIDO, is the crypto that is used when you use your Touch ID, Face ID, implementing in the secure enclave of your phone. So there are different frameworks from Bravos, Cartridge, Obvious, Argent, and of course Ledger Innovation. You can solve governance problem by implementing multi-party computation protocols such as the MUSIC2 protocol, which is used to perform, for instance, Lightning, or if you want to have a threshold management of your security without implying the need of a trusted HSM. So implementing quantum resistance, for example, use the Falcon algorithm as signature. In heritage, it can, okay, basically all those use cases are enabled by account abstraction. But for the coffee, I like get it yourself. Okay, so now just a brief word about passkeys. So passkeys is a way to have a streamlined signing without passwords, because handling password is a pain. Okay, we all have this seed and this beep to manage all those words to keep somewhere. There are some attempts to manage it that could be discussed. But okay, using passkeys could be a way to onboard a user by simply making something really familiar as you make your Face ID, you have your password, which is used as your secret key for your signing mechanism. So this is the easiest possible crypto onboarding from a mobile web browsers, and actually the keys are stored in the host secure enclave, which is really good. It provides a phishing resistant mechanism. It's still malware prone because we don't have a secure screen on our mobiles, but that's a very good start. And at Ledger, our idea is to reverse the way that we are usually working. to onboard first using a very easy user experience, and maybe straighten later when the stakes are worthy, and then convince the user to add a hardware wallet to his security perimeter, to have the anti-malware feature that you have with a hardware wallet. Okay, so to do this, we want to implement WebAuthn, but WebAuthn requires to perform non-native elliptic curve computations. And from what we found when we began to work on it, it was like 300 times more expensive in Cairo or Solidity than using a native computation. So mainly, this would kill all the benefits that we could have using a layer 2 to have such a huge factor. Okay, so from here, there are two solutions. So the easy way would be to just introduce a new precompile. And the hard way is to optimize things a bit. And as I need to work, that's what we'll talk now. So implementing such a mechanism in a smart contract language is a bit different from what we do usually when implementing cryptography. Mainly, there are very exotic feature in Solidity. For example, modular multiplication and addition have the same cost. Memory cost model also are very specific. And we have less available implementation of all those mechanisms. Okay, so let's dip a bit into detail now. So mainly, what you need to know about elliptic curve cryptography, you just need two operations: addition, okay, and multiply the point by a scalar. That's it. So like the operation you have on a vectorial space. Mainly, the keystone of all elliptic curve cryptography is point multiplication, because multiplying a point is easy, but extracting the scalar from the knowledge of the results, which is known as the elliptic curve discrete logarithm, is intractable. And this operation is what you use when you derivate your private key to your public one. It's a multiplication. And when you verify your signature, you perform double multiplication and addition, which we will refer as mulmulad. Okay, and this is very expensive, and this is 98% of cryptographic protocol in average. So first, we perform a systematic bench of the Solidity implementations they were in the wild. You have the result here. So, for instance, Orbs network, I think that's the one maybe Opclave used when they claim their 1 million gas cost. There are more efficient implementations. Actually, the best one is from Obvious Tech, and Alembic introduced the idea to use precomputation to speed up things. So we did. So we use a lot of tricks. First, we revisit all coordinate systems. As said before, it's unusual to have multiplication and addition having the same cost. So it's not usual specialized Jacobian that were the most efficient. So we used another one. So we had again here. We used a multi-base exponentiation. So semimulad is known as Charming streak. It's a very classic one. It's used in OpenSSL and all classic cryptographic library. It's a way to have a double multiplication for the cost of one. And what we did is we extended to 8 pre-computed bases, splitting each of the input P and Q into four values, leading to 16 kilobytes of pre-computation to again forecast to 75%. But in reality, as memory access are expensive, we also had to optimize this. So basically there is a cold and warm access cost when using a storage load or Xcode copy. So Xcode copy is a classic trick, and there is non-contract to use it to improve the cost. And actually, what we did, we reused this idea to use code copy instead by overwriting for each user. It's publicly into the contract, enabling the fact to use code copy instead of Xcode copy. And several other tricks, so implementing everything in assembly, inlining because compiler was not so good, and so on. And finally, we reach five times faster implementation. That's the best previous one. So here are our results. There are here two proposed implementation. Without pre-computation, we reach 200 kilos gas, and with pre-computation, 61. So we think that with these numbers, signing is as expensive as a single mint, and maybe there is no need for precompile. And also, by analyzing the other library, we found some vulnerabilities. So this also highlights the point that, account abstraction will introduce the possibility to change your crypto, but you have to be very careful because it is really easy to make mistakes, and mistakes could lead to a fatal vulnerability. For instance, before our PR, it was possible to steal all currencies from obvious stake implementation. So to wrap up things, we achieve a 5 times cheaper gas cost. We systematically bench and review all Solidity code we found. We made some PR on Bravo, so this is Cairo implementation. And there are all the technical details on a paper which is available on the e-prints, and you will have the link later. And as further work, we still are working on further trade-off from the 30 million first deployment cost to zero. There are further trade-off. We aim at benching and this work on different layer 2s, and we are also working on MPC implementations. So here is a link to the paper. It is also linked to the GitHub repo. And if you have any question.
Thank you. Do you think this also apply to things like Peterson hashes?
Yes, of course.
Thanks.
Yeah, simply you just have to split the 4 points each into 2, and you can use a multi-base experimentation as well. Sure.
Thanks. Could you please also explain what is the precomputation that you did on your implementation? The 3.2 megabytes or?
Yep, I would advise you to go into the paper because you will have all the formulas, but mainly the idea here is that, in fact, instead of splitting as a window, what you can do is, for instance, so the 2 points are the public generating point of the elliptic curve and the public key. You can split it into those are power of 2 multiplied by each point, and this way, instead of having just 2 points in your in Shamir, you can have 8. So it's like cutting. It's not only using one scan of the full size of the operand. It's a fourth of the length of the operand that is performed, because using on Alembic repo like that, there is scanning of 256 bits in only one loop. Okay, this is a classic Shamir. Using 8 bases, you can do it by scanning only 64 bits. Okay, this is a 64-bit loop. So the asymptotic complexity is cut by 4.
Someone want to ask another question? Okay, it's okay. Thank you, Renaud. And now I will let you enjoy a little break before the next conference. Thank you very much. Thank you, Renaud.